Dear viewers, in the series on non-aqueous solvent, we have discussed what are non-aqueous solvents and how are they different from the aqueous solvent, that is water. We have studied various physical and chemical characteristics of non-aqueous solvents along with the reactions which takes place in the non-aqueous solvents. Among the examples of non-aqueous solvents, we have discussed liquid ammonia, liquid hydrogen fluoride and liquid SO2 in detail. In today's lecture, we will be discussing one more example of non-aqueous solvent, that is N2O4, that is dinitrogen tetraoxide, and also we will be discussing one more non-aqueous solvent which is molten salt along with its applications. So, let us proceed with the lecture. So, let us take a quick look at the lecture plan. So, the lecture plan goes this way. First of all, we will be discussing the solvent dinitrogen tetraoxide, then we will discuss its structure, the physical and chemical properties of dinitrogen tetraoxide, then the uses of dinitrogen tetraoxide. Thereafter, we will be discussing the molten salts and their applications. Coming on to the physical properties of dinitrogen tetraoxide, which is N2O4. It is an ionizing solvent, that is, it undergoes autoionization. It is a non-protic solvent. Non-protic solvent is a solvent which does not contain any hydrogen in its molecular formula, and we can see from the molecular formula of dinitrogen tetraoxide, it is N2O4. It does not contain any hydrogen, and therefore, it is a non-protic solvent. Solubility. It is a poor solvent for ionic compounds due to low dielectric constant, which is only 2.42 at 273 Kelvin, but it is a good solvent for organic compounds. As we all know that the Coulombic force of attraction between the ions is inversely proportional to the dielectric constant. Since the dielectric constant is very low, that means the value of force of attraction between the ion is high. Since the force of attraction between the ion is high, so this the solvent, that is N2O4, it does not easily get ionized, and hence it does not remain in the polar form. So, being non-polar, it dissolves a non-polar compounds. Therefore, it is a good solvent for organic compound, or we can say for covalent compounds, and it is a poor solvent for ionic compounds. It is also a good solvent for reducing agents and a powerful oxidizing agent itself. Explosive reactions occur with reducing agents. That means, when a reducing agent is dissolved in N2O4, because it is a powerful oxidizing agent, so the reaction which takes place, it is in the form of explosion. It can be easily prepared and purified. So, this is the plus point of using N2O4, that it can be easily prepared and can be easily purified. It has convenient liquid range, that is from minus 12.3 degrees Celsius to 21.3 degrees Celsius. So, it remains liquid between this range. At a temperature below 12.3 degrees Celsius, it remains in solid form, while at a temperature above 21.3 degrees Celsius, it remains in gaseous form. So, to use it as a solvent, we have to use it between this temperature. N2O4, it undergoes autoionization, though the autoionization is poor due to low specific conductance, and on autoionization it gives a nitrosyl ion which is NO positive plus a nitrate ion which is NO3 negative. Since the autoionization is poor, but it can be enhanced by the solvents of high dielectric constant like nitromethane. It means that if we add nitromethane or any other solvent with high dielectric constant, its autoionization can be increased. This is the tabulated form of the physical properties. So, from here we can see that the molecular formula is N2O4, its molar mass is 92, its appearance is colorless liquid, that means in liquid state it is colorless, while in the gaseous form it has orange color. Its density is 1.442 gram per centimeter cube at 21 degrees Celsius. Its melting point is minus 12.3 degrees Celsius and its boiling point is 21.3 degrees Celsius. Its dielectric constant is 2.42 at 273 Kelvin. Its electrolytic conductance is 2 into 10 to the power minus 13 at 290 Kelvin. Coming on to the structure of N2O4. The molecule of N2O4 is angular in shape with ONO bond angle, that is, this is oxygen, nitrogen, oxygen. The bond angle here, ONO bond angle is 132 degrees, and the bond length of oxygen and nitrogen, this ON bond length, this is 1.20, and the bond length of all the 4 ON bond is equal, which is equal to 1.20, and this bond length is intermediate between a single and a double bond. We can see from here that it has on one nitrogen we can see it has one single bonded oxygen and one double bonded oxygen, but it is resonance stabilized, and this double bond is not stuck to one position, but it keeps on rotating. So, we can say it has partial double bond character, which is intermediate between the single and the double bond, which is more than a double bond and less than a single bond. Hence, the bond length is also intermediate between the double and a single bond. By X-ray diffraction on solid N2O4, it shows that the structure is planar. That means, all the 6 atoms, 4 oxygen and 2 nitrogen, these lies on one plane. And this nitrogen bond length is very long. So, the bond is weak, since it is significantly longer than the average NN single bond length. So, this bond is weak. The bond length is between N and N is 1.45 angstrom. Dinitrogen tetraoxide, that is N2O4, it decomposes to nitrogen dioxide, that is NO2, in a first order process. So, we can see from this reaction that N2O4 it decomposes to give 2NO2, and this is a first order reaction. Coming on to the chemical reactions of dinitrogen tetraoxide. The first one is the acid base reactions. Acids are the substances which furnishes the nitrosyl ion, that is NO positive ion. Example, NOCl and NOBr. So, we can see from the structure that on dissociation NOCl will give NO positive plus chloride ion, and NOBr will also give NO positive, that is a nitrosyl ion and a bromide ion. So, therefore, these acts as an acids. On the other hand, bases are the substances which furnishes the nitrate ion, that is NO3 negative ions. Example, AgNO3, which on dissociation will give Ag positive plus a nitrate ion, NO3 negative. So, we can see the reaction. Acid plus base will give salt plus solvent. This is a neutralization reaction, and NOCl acts as an acid and AgNO3 is a base. So, these two react together to give a salt, which is AgCl plus the solvent N2O4. Second is the reaction with metals. Very active metals like alkali metals, they react with liquid N2O4 similarly as water. So, we can see from the reaction, the metal M is here the alkali metal, it reacts with N2O4 to give NO plus MnO3 metal nitrate. Like water, it reacts, it gives metal hydroxide and releases hydrogen. Like addition of HCl in water increases the reactivity of water towards metal. Similarly, the addition of NOCl, which behaves as an acid because it furnishes NO positive ion, that is the nitrosyl ion. So, on addition of this NOCl to liquid N2O4, it increases the reactivity towards metals. So, here we have example, zinc, when it is added to NOCl in liquid N2O4, it gives zinc chloride. This is the second example where tin, when it is dissolved in N2O4 and NOCl is added, so the reactivity of this tin is increased. Like in water, we have metal, and if we add HCl in water, then the reactivity of this metal increases. So, similar is the case with N2O4 also. Next is complex formation reactions. Complex formation reactions are not very common in case of N2O4, but the reactions taking place are similar to those taking place in water. Liquid ammonia and liquid SO2. That means, the type of reaction which take place in water or liquid ammonia or liquid SO2, similar type of reaction also take place in N2O4. So, we have here zinc nitrate, which is in solid form. When it reacts with diethyl amine nitrate, then it in liquid N2O4 it will give diethyl ammonium nitratozincate complex. A complex is formed. Next is the solvolytic reactions. Solvolytic reaction means that the solvent molecule, it dissociates into the cation and anion. Like in case of N2O4, it on autoionization it gives a nitrosyl ion and a nitrate ion. So, one of these ions or even the both, they react with the solute to give the product. So, these are known as solvolytic reactions and these are also known as solvolysis. Lithium carbonate is solvolized in liquid N2O4 in the presence of traces of water. So, here is the reaction. We have lithium carbonate plus N2O4. These two react together to give lithium nitrate plus N2O3 plus carbon dioxide is released. Similar type of reactions takes place if we use calcium carbonate or zinc carbonate, calcium oxide, zinc sulphide, sodium carbonate or sodium hydroxide. And the reaction takes place rapidly in presence of trace of water. That means we can speed up the reaction if we add little amount of water in the reaction medium. Aluminium chloride on solvolysis forms a mixture of aluminium nitrate and aluminium nitrate dot N2O4. Diethyl ammonium chloride is solvolized as, this is diethyl ammonium chloride on solvolysis, that is on reaction with N2O4 it gives diethyl ammonium nitrate plus NOCl. We have some other example of solvolysis that are like KCl on solvolysis in N2O4 it gives KNO3 plus NOCl. Magnesium ClO4 whole twice in N2O4 on solvolysis it gives magnesium nitrate plus NoClO4. Hexaaqua magnesium chloride it gives hexaaqua magnesium nitrate plus NoCl. So, solvation reaction means that the solute molecule is surrounded by a number of solvent molecules to form the addition compound. So, a number of compound undergoes solvation in liquid N2O4 to form solvates. Like for example, copper metal with liquid N2O4 it forms a solvate with the formula CuNO3 whole twice dot N2O4. Similarly, zinc, aluminium and uranium oxide forms zinc nitrate dot 2N2O4, this is a solvate of N2O4, aluminium nitrate dot N2O4 and UO2 nitrate dot N2O4. So, these are the solvates. Some organic solvent also form solvates with N2O4. Like for example, we have dioxane, it forms white crystalline complex with the formula N2O4 dot O CH2 CH2 whole twice O. Tetrahydrofuran, which is THF, it forms C2H8O dot N2O4 and 2C4H8O dot N2O4. Ether forms 2R2O dot N2O4. So, these are some examples of the solvates of organic compounds. Coming on to the uses of dinitrogen tetraoxide. N2O4 is used as a catalyst in the manufacturing of sulfuric acid by the lead chamber process. It is also used in the production of nitric acid by hydrolysis and it is also used as a oxidizing agent. The next topic, or we can say the last topic of this series, is the molten salts. So, what are these molten salts? The chemistry of the molten salt as non-aqueous solvent system is one of the important development in the inorganic chemistry. The difference in molten salt and aqueous solvent is that the solvent has strong bonded and stable nature and higher concentration of various species can be obtained in saturated solution of water. So, before going to all this, let us first of all see what are molten salts. Molten salts are nothing but simply a salt in the molten form, that means in the liquid form. Any salt if we take in the liquid form, it is called molten salt and it behaves as a non-aqueous solvent. On the basis of the structure of the liquid, molten salt can be classified into two groups. Group 1 involves those compounds like alkali halides that are bound chiefly by ionic forces. We know in alkali halides like NaCl, the bond between the sodium ion and the chloride ion is ionic bond. So, group 1 involves compounds with, or we can say it involves the ionic compounds. On melting, a very little change takes place in these materials, and what are the changes? Like the coordination of the ion drop from 6 in the crystal to 4 in the melt. That means, if we look at the crystal of some alkali halide, as for example, if we take NaCl, so we see that sodium ion, it is surrounded by 6 chloride ion. That means a positive ion is surrounded by 6 negative ion. Similarly, a negative ion is surrounded by 6 positive ion. So, the coordination number is 6 because one ion is surrounded by 6 ions of opposite charge. But when this crystal or the solid lattice, it is melted, it is brought into the molten form, it becomes molten salt. Here what happens? The coordination number falls to 4. That means now one positive charge is surrounded by 4 negative charge, and the vice versa. That means one negative charge is surrounded by 4 positive charge. So, this is one of the difference which takes place. Second is long range order found in the crystal is destroyed. That means long range order means if we look at a crystal which is in the solid form, throughout the crystal it is very orderly arranged. Everywhere a single positive atom, or we can say a single positive ion, is surrounded by the same number of negative ions. Suppose it is 6, the coordination number is 6. So, we can say the positive ion is surrounded by 6 negative ion throughout the crystal. Similarly, the negative ion will be surrounded by 6 positive ion throughout the crystal, and this order persists throughout the crystal. So, we call it long range order. But in case of melt, that means when this solid is brought into the molten form, what happens? This long range order is disturbed, but only a local order exists. Local order, that is, a cation is surrounded by anion and the anion is surrounded by cation. They can be like one cation is surrounded by 2 anions, or 2 cation can be surrounded by 4 anions. So always there will be that cation is surrounded by anion. On the other hand, anion will be surrounded by cation, but the number is not fixed. So, long range order does not exist. Coming on to the characteristics of molten salts. These are fused salts and these are good electrolytes because of the presence of large number of ions. So, in molten salts, because it is salt, so it will have a cation and an anion, and in molten form the bond has been broken. So, we have free ions, and therefore, it is a good electrolyte. These behaves normally with respect to cryoscopy. Cryoscopy means at low temperature these behaves normally. Group second are the compounds in which covalent bonding is important. So, in group 1 we have discussed the ionic bonding, and in group 2 are the compounds which have covalent bonding. These compounds tend to melt with the formation of discrete molecule, though autoionization may occur. That means, in case of group 1 where we were discussing the ionic compounds, the ionic compound, it breaks into ions. Suppose we have NaCl, it will give Na positive and Cl minus ion. But in case of group 2 which involves covalent bonding, so a big molecule, it will break into small discrete molecules. So, this is the basic difference between the group 1 compounds and group 2 compounds. Here autoionization may also occur. Mercury halide, it ionizes as follows: HgX2, it gives HgX positive plus HgX3 minus. So, this is the autoionization of HgX2 molecule. If aluminum chloride is added to an alkali metal chloride melt, an alkali metal tetrachloroaluminate is formed. We have this is the example here: metal chloride, this reacts with aluminum chloride to give metal plus aluminum chloride. So, the tetrachloroaluminate ion, that is AlCl4 minus, it undergoes autoionization, and on autoionization it gives Al2Cl7 positive, the cation part, and Cl minus, the anion part. The basicity can be easily related to the concentration of the Cl minus ion. So, from the concentration of Cl minus ion, that is how much amount of Cl has been released, we can easily calculate the basicity of AlCl4 minus. The term molten salt conjures up images of high temperature fuse system. That means if we hear the term molten salt, the image in our mind is that something is in a very high temperature. Any salt, it has been brought to a very high temperature and then it is converted into the melt. But this is not always true. There are some salts which are liquid at room temperature. For example, when alkyl pyridinium chloride are added to aluminum chloride, the resultant compound are similar to alkali metal tetrachloroaluminates, but they are in the liquid form. So, this is the example. So, this is a salt here. When we add Al2Cl6, it forms a complex and this complex is in the liquid form. So, it is a molten salt which is liquid at room temperature. The room temperature molten salts are the simple molten salts which remain in the liquid state at room temperature. We need not raise the temperature too much. The chemistry of these molten salts are similar to those of metal aluminium chloride, tetrachloride we can say. The only difference is that these can be carried out at room temperature, but MAlCl4 require high temperature. So, the salt we have just now discussed, the previous example, this is in the melted form at room temperature, but if MAlCl4, where M is any alkali metal, if we have to bring it to the melt that is to the molten form, it requires high temperature of about 175 degrees Celsius. Another example, we have a mixture of crystalline solid, that is triethyl ammonium chloride plus copper 1 chloride. So, when these two they react together, an endothermic reaction takes place. That means we have to give heat to this reaction and it gives a light green oil, a product which is of light green color and it is oily in nature. And this light green color is due to the coordination of a second chloride ion to copper ion to form dichlorocuprate first ion. So, this is the reaction. We have triethyl ammonium chloride. When it reacts with CuCl, it gives this particular complex and this complex is light green oil. The low melting point of the above light green oil is due to the following equilibria. Here we can see that we have CuCl2 negative plus CuCl, it remains in equilibrium with Cu2Cl3 minus. In the second equilibrium, we can see two molecules of CuCl2, they remains in equilibrium with Cu2Cl3 negative plus Cl negative. Then we have CuCl2 negative plus Cl negative, it remains in equilibrium with CuCl3 2 minus. So, we can say that this particular system, it contains 4 anionic species and the impurities, that means because it has 4 anionic species, so the extra one are the impurities, these accounts for the depression in melting point. That means due to this, these 4 ionic species, or we can say anionic species rather, the melting point is quite low. So, it remains in the melted form at room temperature. Therefore, the material is oily and it never forms a crystalline solid with a true freezing point, but it congels to a glass at about 0 degrees Celsius. That means at a temperature at about 0 degrees Celsius, it converts to a glassy form, but it never forms a pure crystalline solid with a true freezing point. The application of above reaction is that this system is used both as a solvent and as a reactant in a voltaic cell. When two platinum gauze electrodes are immersed in liquid chlorocuprates and a potential is applied, the cell begins to charge. And the half cell reaction are CuCl2 negative, it takes an electron, that means it is reducing. This is the reduction reaction, it forms copper plus 2 chloride ion. The second reaction is CuCl2 minus, it forms CuCl2 plus electron, it releases an electron, therefore, this is the oxidation reaction. Other application of molten salts, many reactions that cannot take place in aqueous medium because of the reactivity of water can be performed in molten salts. Example, chlorine and fluorine in water, they react with it and form hydrogen halide. So, the reactivity increases with water, but this can be easily performed under, or we can say, in the molten salts. So, the use of molten halides obviates this problem. That means, if we use molten halides instead of water, this problem can be removed. The molten halides are also used in the preparation of the halogens. Here we can see we have KHF2. This gives on electrolysis fluorine plus hydrogen plus Kf. So, the fluorine can be prepared with this reaction, and NaCl on electrolysis it gives Cl2, that is the chlorine gas, plus sodium. So, chlorine can be prepared by this reaction. So, we can say that the halogens can also be prepared using molten halides. So, these halides are in the molten form. Also important, the molten salts are also important in commercial production of sodium, as it is extremely reactive to coexist with water. We know that sodium, when it comes in contact with moisture or water, it catches fire because hydrogen is released. So, we cannot prepare sodium in water, but this can be done with the help of molten salt. It is also used in the production of magnesium and aluminium, and in the removal of silica impurities by a high temperature acid base reaction. So, from this reaction we have gangue, which is SiO2 plus calcium oxide, which is called flux. These two give together to form slag, that is calcium silicon O3. One of the important aspects of molten salt chemistry is the readiness with which the metal dissolves. The alkali metal halides dissolve large amount of the corresponding alkali metal, and some system like cesium and cesium chloride are completely miscible at all temperature above the melting point. So, we can say that if we have the alkali metal halide in the dissolved form or in the melted form, a good amount of metal can be, we can obtain a good amount of metal in the dissolved form, but this is not done if we have alkali metal halide dissolved in water. On the other hand, the halides of zinc, lead and tin dissolve such small amount of the corresponding free metal that special analytical techniques must be devised in order to estimate the concentration accurately. That means, if we dissolve these metals halide, so only a very little amount of these metals are obtained in the solution form, and we need some special technique to obtain them accurately. Molten salts provide a medium in which the concentration of the anionic ligand can be much higher than in the aqueous solution. For example, the concentration of chloride ion in concentrated aqueous solution is 12 molar. That means, if we dissolve chloride ion in any form in water, so the maximum concentration which can be obtained is only 12 molar, but the concentration of the chloride ion in molten lithium chloride is 36 molar. So, this is 3 times more than which is obtained in aqueous medium. Also, there are no other competing ligands like water present to interfere. So, this is one of the plus point of using the molten salts instead of aqueous solution. Therefore, it is possible to form complex ion that are well known in aqueous solution. We have cobalt chloride plus chloride ion, it reacts with chloride ion to form cobalt tetrachloride 2- ion. And also those that cannot exist in aqueous solution because of their susceptibility to hydrolysis. So, these ions, these cannot exist in aqueous form because these are susceptible to water, that means these undergo hydrolysis, but these can exist in molten form. We have FeCl2 plus chloride ion, it gives FeCl4 2-, chromium chloride plus 3Cl-, it gives chromium hexachloride 3-. We have titanium chloride plus 3Cl- ion to give hexachlorotitanium 3- ion. So, this was all about the molten salt. Coming on to the summaries of today's lecture. Today we have discussed the solvent, which is a non-aqueous solvent, dinitrogen tetroxide. We have discussed its structure, the physical and chemical properties of N2O4 and its uses. Then we have discussed the molten salts and their application. So, this was all about the non-aqueous solvent. In this series on the non-aqueous solvents, we have discussed the non-aqueous solvents and we have compared them with the aqueous solvent. We have also discussed the characteristics of non-aqueous solvent, their classification, and we have taken some examples in detail like liquid ammonia, liquid SO2, hydrogen fluoride and N2O4. Apart from this, we have also discussed one more non-aqueous solvent, that is the molten salt. So, this was all about the non-aqueous chemistry. Thank you.